Dear students, in this class, now let us discuss an important theorem, which is known as mean value theorem. Theorem is mean value theorem. What is mean value theorem? Here, the theorem states that if f is continuous on closed AB, f is continuous on closed interval AB, G is integrable on closed interval AB, such that g of x greater than or equals 0, g of x greater than or equals 0 for all x, then there exists a point C for an open interval AB such that integral a to b f of x into g of x dx equals f of c into integral a to b g of x dx. So this is the mean value theorem. We already know that another Lagrange's mean value theorem. That theorem states if f is continuous on closed AB, which is differentiable on open AB, then there exists a point C for an open interval AB such that f dash c equals f of b minus f of a by b minus c. That is the slope of a point at which which is same as the chord joining as the end of the slope of the chord joining the end of the points. So here, if f is continuous on closed AB and g is integrable on closed interval AB with g of x greater than or equals 0 for all x, then there exists a point C for an open interval AB such that integral a to b f of x g of x dx is nothing but f of c into integral a to b g of x dx. How to prove this one? The proof is, since g is continuous on closed AB and f is continuous on closed AB. F is continuous on closed AB means f is continuous on closed interval AB means f is bounded, means mod f of x less than or equals some capital K. Since f is bounded, its supremum and infimum exist. So let m equals the supremum of f of x, where x fall in closed interval AB, and small m equals infimum of f of x, where x fall in closed interval AB. Why? Because f is bounded. So we know that m less than or equals f of x less than or equals capital M. Agree? So that should imply m into g of x or m into integral a to b g of x, or simply m into g of x less than or equals f of x into g of x less than or equals capital M into g of x. Okay? So that means m into integral a to b g of x dx less than or equals integral a to b f of x into g of x dx less than or equals capital M into integral a to b g of x dx. Enough? Okay. Now it is given g of x greater than or equals 0. If g of x equals 0, what happens? So the results fall immediately. Agreed, there is nothing to show. If g of x differs from 0, suppose g of x differs from 0, then you can divide throughout by g of x, integral a to b g. When g of x differs from 0, clearly integral a to b g of x dx differs from 0. Enough. So you can divide this equation 1 throughout by integral a to b g of x dx. So what do you get? So this gives m into, if you divide it is m less than or equals integral a to b f of x into g of x dx all divided by integral a to b g of x dx less than or equals capital M. Agreed. Suppose this is k. So that means it is m less than or equals k less than or equals capital M, where k is integral a to b f of x g of x dx by integral a to b g of x dx. Then by intermediate value theorem, there exists a point C fallen open interval a b such that f of c equals k. Okay, that means what is f of c? F of c is integral, that is f of c equals, what is k? K means integral a to b f of x g of x dx all divided by integral a to b g of x dx. So finished. So this gives integral a to b f of x g of x dx is nothing but f of c into integral a to b g of x dx. Clear? Yes, which is that is known as the mean value theorem. So the theorem states when f is continuous on closed AB, g is integrable on closed AB, then with the if g of x greater than or equal to 0, then there exists a point C fallen open interval AB such that integral a to b f of x g of x dx is f of c into integral a to b g of x dx. Okay. Now, suppose g of x equals 1. What happens here? If g of x equals 1, what happens here? Then the result becomes integral a to b f of x dx equals f of c into integral a to b 1 dx. Agreed? That equals f of c into integral a to b 1 dx means it is b minus a. So when g of x equals 1, the result reduces to integral a to b f of x dx is f of c into b minus a, where c lies in between a and b. Okay? Right. So this is the mean value theorem. The theorem is so important. Now let us discuss another important result which is known as Taylor's theorem. Taylor's theorem. So the theorem says that if f dash, f2 dash, etc. fn means nth derivative of f are continuous at a, a particular point a, are continuous at this particular point a, then f of b equals f of a plus f dash a by 1 factorial into b minus a plus f2 dash a by 2 factorial into b minus a whole square plus etc. plus fn a by n factorial into b minus a whole power n plus rn, where this rn is known as the remainder of Taylor's theorem. Rn is known as the remainder of Taylor's theorem. If f dash, f2 dash, etc. fn, that is the nth derivative of f, are continuous at a, then f of b is f of a plus f dash a by 1 factorial into b minus a plus f2 dash a by 2 factorial into b minus a whole square plus etc. plus fn a by n factorial into b minus a whole power n plus r, where rn is known as the Taylor's remainder or remainder of Taylor's theorem. How to prove here? Where rn is given. What is rn? Where rn equals 1 by n factorial into integral a to b minus t all power n into f n minus 1 t dt. So this is the remainder. Rn equals 1 by n factorial into b minus t all power n into f n minus 1 t dt. How to prove this one? So to prove this result, now let us start from this remainder. What is Rn? Rn is given, which is 1 by n factorial into integral a to b minus t all power n f n minus 1 t dt. That means Rn equals 1 by n factorial into, it is integral a to b, b minus t all power n into derivative of fn t dt. Okay, fn minus 1t means n minus 1t means derivative of fn t. Agreed? Okay. So, which equals, now by using integration by parts, what do you get? On integration by parts, we have Rn equals 1 by n factorial into, says first function. First function into means b minus t all power n into integral of second. Integral of this one means fn t from where to where? A to b minus integral of derivative of the first function. Integral of derivative of the first function means it is n into b minus t all power n minus 1 into derivative of minus t is minus 1 into integral of second, that is fn t dt. Okay, so that implies Rn equals 1 by n factorial into, if you applies the lower and upper limit, when t equals b, first term vanishing, second term it is minus b minus a into all power n fn a. Okay, if you apply upper limit, it is 0 minus lower limit, b minus a minus b minus a all power n into fn minus n by n factorial. 1 by n factorial into n. N by n factorial means 1 by n minus 1 factorial into integral a to b, b minus t all power n minus 1 minus of minus plus fn t dt. Okay. So that implies Rn equals 1 by or minus of b minus a all power n fn a by n factorial into n factorial plus, again integrate. If you apply this integration here successively, integrating successively, what you get? Then the next term is minus of b minus a all power n minus 1 by n minus 1 factorial into n minus 1 a plus 1 by n minus 2 factorial into integral a to b, b minus t all power n minus 2 into fn minus 1 t dt. Okay, if you apply this process to this integral, then you can apply this process successively. Successive integration by parts on the last term. So what you get? Finally you have this Rn equals minus of b minus a all power n into fn a by n factorial plus the next term is b minus a all power n minus 1 by n minus 1 factorial into fn minus 1 a plus etc. plus last term 1 by 0 factorial into integral a to b f dash t dt. Okay, f dash t dt. When n equals 2. Okay. So it is integral a to b f dash t dt. So that means Rn equals minus of, so that is integral a to b f dash t dt. Since f is integrable on I, so what is integral a to b f dash t dt? We know that it is f of b minus f of a, the last term, which is nothing but f of b minus f of a. Okay, so means Rn equals f of b minus f of a plus b minus a all power n, minus s plus b minus a by 1 factorial into f dash a plus b minus a whole square by 2 factorial into f2 dash a plus etc. and so on. Therefore, putting f of b on that one, so f of b equals f of a plus f dash a by 1 factorial into b minus a plus f2 dash a by 2 factorial into b minus a whole square plus etc. plus fna by n factorial into b minus a whole power n plus rn. Agreed? So finished. So this is this is Taylor's theorem. So the Taylor's theorem is important. When the f has continuous nth derivative at the point a, then f of b is f of a plus f dash a by 1 factorial into b minus a plus f2 dash a by 2 factorial into b minus a whole square plus etc. plus rn, where rn is 1 by n factorial into integral a to b minus t whole power n fn minus 1 t dt, which is known as the nth remainder of the Taylor's theorem. Agreed? Okay. So now let us consider a definition, that is integral as a limit. Integral as a limit. We know that integral is what is integral? Sum of the as a limit of number of certain intervals. Then integral as a sum means that I consider an interval I equals closed interval a. Let define f from I to 1. F from I to 1 is a bounded function. F is bounded. Let p equals a equals x naught, comma x1, etc. xn equals b, be a partition of closed interval ab, and let us epsilon k fall in closed interval xk minus 1 xk. Let epsilon k fall in xk minus 1 xk for k equals 1, 2, 3, etc. up to n. K equals 1, 2, 3, etc. to n. Then the sum. Consider the sum SPF. The sum FPF equals sigma k ranges from 1 to n f of epsilon k into delta xk. F of epsilon k into delta xk, which is called the Riemann sum. It is called the Riemann sum. So this is an important definition. What is the Riemann sum of a function? I is a closed interval which has a partition P. Then for any point epsilon k fall in xk minus 1 xk, where k is 1 to n, then the Riemann sum is defined as Riemann sum for the function f with respect to the partition P is defined as SPF equals sigma k ranges from 1 to n f of theta k delta xk. Okay, so this is an important definition. SPF is known as the Riemann sum of this function f, which is defined on an interval I having the partition P at the point theta. Agreed? Okay. Now, what is capital M K? We know that capital M K is supremum f of x. Supremum f of x, where x fall in closed interval xk minus 1 xk. Since f is bounded, it has both upper and lower limits. Then mk is supremum of f of x, and small mk is infimum of f of x, where x fall in closed interval xk minus 1 xk. Okay, so we know that mk less than or equals f of x less than or equals capital M K. Moreover, it is mk less than or equals f of epsilon k less than or equals capital M K, where this epsilon k fall in closed interval xk minus 1 xk. Sure? That means mk into delta xk less than or equals f of epsilon k into delta xk less than or equals capital M into delta xk. Agreed? That means sigma with respect to k small mk delta xk less than or equals sigma with respect to k f of theta k delta xk less than or equals f of theta k delta xk less than or equals sigma with respect to k capital mk into delta xk. What about the term on left side? Which is LPF. That is LPF less than or equals, what is the middle term? Which is SPF, the new defined term, less than or equals, what about the right side? Which is UPF. So we have this result. If P be the partition of closed interval AB and F is a bounded function, if SPF remains sum, then this result holds LPF less than or equals SPF less than or equals UPF. Clear? Yes. Now there is another result that with respect to this remains sum. The theorem says that let I equals closed interval A. Let I equals closed interval A. F from I to R. Define a function f from I to R which is integrable on I. Then for any epsilon is positive, there exists a partition P of closed AB such that there exists a partition P epsilon of I means P epsilon of closed AB, and if P is any partition of R, P epsilon be a partition of I, P be a partition of R, means what is P? Listen, I is closed AB, F from I to R is integrable on I, P epsilon is any partition of I as well as P be a partition of R, I be a subinterval of R, P be a partition of R, P epsilon be a partition of I. That means this P be the refinement of P epsilon. Then modulus of SPF minus integral A to B of strictly less than epsilon. So this is an important result. I equals closed AB, P epsilon be a partition of I, P be a partition of R. Since I be a subset of R, P acts as the refinement of P epsilon. Then for any function, integrable function f from I to R, modulus of SPF minus integral A to B of less than epsilon. What is SPF? That is the remain sum. What is remain sum SPF? Sigma with respect to k, f of theta k, delta x